Ferns and their relatives dominated Earth for 100 million years, building forests so vast their remains became the coal that powers modern civilization. This is the story of the spore-bearers, the plants that perfected life on land before seeds even existed. What if the most successful plants in Earth's history are the ones we dismiss as primitive? Ferns, horsetails, club mosses. We see them as evolutionary leftovers, relics, the plants that lost to flowering species. But for over 100 million years, they were the undisputed masters of Earth. They built forests that made modern rainforests look sparse. They grew to sizes that would dwarf most trees today. They covered continents so completely that when they died, their remains formed layers of carbon hundreds of meters thick. We call those layers coal. Did you know that almost every piece of coal humans have ever burned came from plants that reproduced with spores, not seeds? This is the age of the spore lords. By the end of this episode, you'll understand how ferns and their relatives conquered a planet, why spores made them nearly invincible for an entire geological era, and what their success tells us about the ruthless efficiency of evolution when conditions are perfect. This isn't just botanical history. This is the story of Earth's first mature ecosystems. Complex, stable, and so productive, they fundamentally altered the carbon cycle for hundreds of millions of years. How does a reproductive strategy older than seeds dominate an entire planet? Carboniferous period, 359 million years ago. The world is unrecognizable from the barren shores of 100 million years earlier. Forests blanket the equatorial regions, not the forests we know. These are alien landscapes of towering club mosses, massive horsetails, and tree ferns reaching 30 meters into humid air. The climate is perfect for plant life. Warm, wet, stable. Oxygen levels are rising toward 35%, the highest in Earth's history. Why does high oxygen matter? Because oxygen is the byproduct of photosynthesis. High oxygen means massive plant productivity. It means ecosystems so lush, so dense that every available niche is filled with green. But it also means something else, insects. Did you know that insect size is limited by oxygen availability? With 35% oxygen in the atmosphere, dragonflies evolved wingspans of 70 centimeters. Millipedes grew to over 2 meters long. The Carboniferous wasn't just the age of giant plants. It was the age of giant everything. And at the base of this alien food web were the spore-bearers, ferns, club mosses, and horsetails that had perfected the art of terrestrial life. But here's the paradox. These plants were still using ancient reproductive methods. No flowers, no fruits, no seeds, just spores. Millions upon millions of microscopic packages scattered on the wind, each hoping to land somewhere wet enough to germinate. How does a primitive reproductive strategy dominate the most competitive environment Earth has ever seen? Modern biology tells us seeds are superior. They carry nutrients, they can survive dormancy. They have protective coatings. Seeds are evolution's advanced technology. Spores are the beta version, simple, vulnerable, dependent on moisture. Yet for 100 million years, spores won. Why? The answer lies in understanding what success means in evolution. It's not about sophistication, it's about fit. And in the Carboniferous, conditions fit spore-bearers perfectly. The climate was stable, warm temperatures, high humidity, predictable rainfall. In these conditions, spores' weakness became irrelevant. There was always moisture. Spores could germinate almost anywhere, and their advantage, sheer numbers, became overwhelming. A single fern can produce 50 million spores per season. A tree-sized club moss, hundreds of millions. Did you know that spores can travel thousands of kilometers on wind currents? Seed plants invest heavily in a few offspring. Spore plants carpet the world with genetic lottery tickets. When every ticket has a decent chance of winning, quantity beats quality. Let's talk about the giants, lepidodendron, the scale trees, club mosses that grew 50 meters tall with trunks a meter wide. They didn't look like modern trees. Their trunks were covered in diamond-shaped scars where old leaves had fallen off, giving them an almost reptilian appearance. At the crown, a burst of narrow leaves photosynthesizing in the dense, humid air. These weren't trees in the traditional sense. They had very little actual wood. Most of their trunk was soft tissue supported by an outer bark-like layer. How does a 50-meter-tall plant stand up with minimal wood? The answer is environment. In the still, humid air of Carboniferous swamps, there was no strong wind. No need for heavy structural support. These trees grew fast, reproduced once, then died. They were the bamboo strategy at giant scale. When they fell into swamps. And here's where the story gets interesting. Swamps are low-oxygen environments. Decomposition happens slowly. Dead plant matter accumulates instead of rotting away. Layer upon layer of dead lepidodendron trunks piled up in swamp basins. Covered by sediment, compressed over millions of years, they became coal. Did you know that the Carboniferous period produced more coal than any other time in Earth's history? Not because plants were bigger, though they were. Not because there was more vegetation, though there was. But because fungi hadn't yet evolved the enzymes to break down lignin efficiently. Wood-rotting fungi that we take for granted today, that decompose fallen trees within years, didn't exist yet. Dead trees just stayed dead, intact, accumulating. For 60 million years, plants deposited carbon into the ground faster than any process could release it back into the atmosphere. It was a one-way valve. Carbon went down and stayed down. What happens when you remove billions of tons of carbon from the air and bury it underground? The planet cooled dramatically. By the end of the Carboniferous 299 million years ago, Earth had plunged into an ice age. Ice sheets covered the southern supercontinent of Gondwana. Sea levels dropped. The warm, humid paradise that spore bearers loved began to disappear. And here's the cruel irony. The spore lords were victims of their own success. They had been so efficient at photosynthesis, so productive, so dominant, that they pulled enough CO2 out of the atmosphere to trigger global cooling. Did you know that atmospheric CO2 levels during the Carboniferous dropped to around 300 parts per million, lower than at almost any other time in the past 500 million years? The climate became seasonal. Dry periods lengthened. Swamps shrank and spore reproduction, which requires moisture, became a liability. What if you're a plant that needs wet conditions to reproduce and the world is drying out? You go extinct. Across the late Carboniferous and into the Permian period, the great spore-bearing forests declined. The 50-meter scale trees disappeared. The giant horsetails vanished. The tree ferns retreated to tropical refuges. The age of spore lords was ending, but their legacy was just beginning. Let's zoom out and see what the spore bearers accomplished. They created deep, complex soils across every continent. Soils rich enough to support diverse ecosystems for hundreds of millions of years to come. They established forest structure, canopy layers, understory, ground cover. They proved that terrestrial ecosystems could be as productive as marine ones. They changed the atmosphere, oxygen surged, CO2 plummeted. They fed the first terrestrial food webs. Insects diversified into thousands of species. Early amphibians and reptiles colonized the land, feeding on that insect abundance. And they left us coal, billions of tons of stored carbon that humans would eventually dig up and burn, releasing in centuries what took millions of years to sequester. Did you know that the Industrial Revolution was powered almost entirely by Carboniferous forests? Every steam engine, every factory, every train, fueled by dead-scale trees and ancient ferns. The spore lords shaped the modern world in ways they could never have anticipated. But here's the deeper question: why did they fail? Not because they were primitive, not because seeds were objectively better. They failed because the world changed, and their reproductive strategy couldn't adapt fast enough. In stable, wet climates, spores are nearly perfect. In variable, seasonal climates, they're a death sentence. Evolution doesn't favor the sophisticated, it favors the fitted. When conditions shifted, the plants that had specialized for abundance in one environment found themselves unable to survive in another. How many dominant species in Earth's history went extinct? Not because they were weak, but because they were too specialized. The answer is most of them. The spore bearers' decline opened ecological space. And into that space came plants with a different strategy. Plants that could reproduce without water. Plants that invested in fewer, tougher offspring. Plants with seeds. These newcomers didn't outcompete the spore bearers in a fair fight. They just survived better when conditions changed. And in evolution, survival is everything. By the early Permian 280 million years ago, seed plants were spreading. Conifers appeared, cycads, seed ferns. The world was transitioning from the age of spores to the age of seeds. But spore-bearing plants didn't disappear. Ferns, club mosses, and horsetails still exist today, over 300 million years later. They're not dominant anymore. They occupy the margins, the wet places, the understory, but they endure. Did you know that modern ferns are more diverse now than they were in the Carboniferous? They found new niches, they adapted. They became specialists in low-light environments where seed plants struggle. The spore lords may no longer rule Earth, but they never truly lost, they just changed kingdoms. The forests of the Carboniferous were dying. The climate was shifting. The age of spore dominance was ending. But buried in those dying swamps was a revolution waiting to happen. Because while the spore bearers were declining, their roots were doing something extraordinary. They were pushing deeper into rock than ever before, shattering stone, releasing minerals, creating soil chemistry that had never existed. And that soil chemistry would enable the next wave of plant evolution, species that could survive in harsh, dry, seasonal environments. Species that wouldn't just conquer wet lowlands, but mountains, deserts, and polar regions. What happens when plants stop needing perfect conditions and start thriving in terrible ones? Next episode, Architects of Soil. How plant roots became Earth's most powerful geological force, breaking bedrock, creating continents of deep soil, and transforming the planet's entire surface chemistry. This is HistoPrimordia, where history comes alive. Thanks for watching. Subscribe now and join us for the next episode story.